Okay, so this is part two. Same problem as we had before. We're going to try to get the same answers to make sure it makes sense, but we're going to do this a little differently. So what I'm going to do is shade in one of these fan blades in our fan. And we want to say, how much does that move in a circle? Well, the distance it's going to go around depends on our radius of our fan. So let's give it a radius. Let's say it is 10 centimeter fan blade. So the point right there that goes around, the distance that it covers, delta x, is going to be r times theta. And then our tangential velocity is going to be r times omega. And then our tangential acceleration is going to be r times alpha. So what we're going to do is try to solve this translationally and then go back. All right, so we're going to use these conversions from these numbers to translational numbers. So here we have 300 revolutions per minute. Our tangential velocity is going to be r omega is, remember, we want to convert this 300 revolutions per minute times 2 pi radians per rev times 1 minute is 60 seconds is going to be 31.4 radians per second. So here we're going to do, our distance r is going to be 10 centimeters times 31.4 radians per second. And now we have a problem. This thing that we're going to calculate is going to be, let's put this in meters, 0.10 meters. We're going to have meters times radians over second. So I'll write it out. V tangential is 3.14 meters per second times radians. Well, that doesn't make a lot of sense. And this is the point I want to get to, is this unit. 1 radian comes from this definition where we're defining the angular distance and the translational distance. So if we rewrite this, we have theta is delta x over r, or s over r. And so the units of this is meters divided by meter. 1 radian is 1 meter over 1 meter. So radians are not a real unit. They're a counting unit. It's like going 1 sheep, 2 sheep, 3 sheep. And it's a ratio. It's always going to be 1 unit of distance divided by some other unit of distance. Right? Consider it a unit conversion. So here, this tangential velocity is 3.14 meters per second times meters per meter. And then they just cancel out. So when I was a new teacher, I would just tell students the radians go away or they come back when you need them. If you're missing something, you look at the dimensions, and if it's an angle and you've canceled out some meters somewhere, then you stick in a radians. But I'm showing you where this comes from is because of our definition of what a radian is. It's not a defined unit, it's a counting unit. So we're just going to make it go away. We're going to cancel it out by putting in what a radian means. And I mean it when I say 1 radian is 1 meter per meter. If I take and I draw a circle, so I'm going to draw this circle. Let me draw it on the inside. I'll pick a center point there. So this distance r, and then in red, roughly this distance is r as well. I'm saying that this arc length is r. Then this angle that's enclosed in here is 1 radian. That's the definition of a radian. So, there's that. So we're going to pause the video for a minute and repair again since I've used up all my paper. Okay, so we've restored things back. We're going to solve this problem, except for the bit where I need that the tangential velocity is 3.14 meters per second. All right, that's just going and doing this stuff again, and this is what we find. All right. So now we're going to solve things in terms of translational variables. All right, this is our V initial. V final is 0 because it comes to a stop anyway. And we're looking for delta x is something, and our acceleration is something, and our time is 10 seconds. If this was a thing that was moving in a straight line, we'd just do one-dimensional kinematics. We'd say, oh, well, delta x is based on our average velocity times our time, is 1/2 times 3.14 meters per second times 10 seconds. And that is going to be, when you get up, 3.14 times 10 divided by 2 is 15.7 meters. And then we would go and say, well, we need the acceleration. That acceleration is based on the change in velocity over time. So we'll have our acceleration is V final minus V initial over t, which is, well, V final is 0, so we'll have minus 3.14 meters per second over 10 seconds is 0 minus 0.314 meters per second squared. So now we'll go and figure out what the angular acceleration and the angular distance is. And our theta is going to be delta x over r. That's the definition of theta, is delta x over r. And our angular acceleration is going to be our acceleration over r by definition. And this is going to be minus 0.314 meters per second squared over r is 0.1 meters. So our theta here, our units, we have 1 meter divided by 1 meter. That is a radian. So we'll have minus 3.14 radians per second squared. Why did I do that? This is alpha. This is angular acceleration. This will be theta. So theta is delta x over r is 15.7 meters over 0.1 meters. 1 meter over 1 meter is a radian. So theta is going to be 157 radians. And when we go back to the problem that we solved before, other than the minus sign I dropped here, we get the same angular acceleration and we get the same distance. And everything else is doing the same conversion the same way. So hopefully that made some sense doing it twice. There are usually two ways of doing a problem. One is to attack it directly to do the angular variables, and the other is to do the conversion, is to go from our angular variables to tangential variables, and then solve the problem as if it were a 1D problem, and then go back. And sometimes it's easier to go that way. Sometimes you know enough stuff, you know enough tangential variables that it's easier to translate the ones you don't know. And other times it's not. Other times you want to do everything Angular. But I wanted to show you both versions of that. All right, so we'll do one more problem, and then we'll see how y'all respond to it. And um, there may be more videos after this, but effectively, this is stuff you've already done, but in Greek.